So let's look at an example of calculating fluid force. What we have here is a triangular plate, so that's a 2D plate that's just been dipped vertically into some fluid there. We're 2 feet below the surface. That triangle is 4 feet tall and the base there is 6 feet. So again, remember the problem is all the way along that plate you're experiencing different pressure because at every depth along there you're at a different depth, therefore different pressure, different force. So our idea is going to be to cut this into thin strips and look at the force, approximate the force on that thin strip, and then add those up and let them shrink. So first, let's put a coordinate system on here. And because this varies with depth, I'm going to make this a 2D coordinate system. I'll call this x in feet, this y in feet, and I'm putting my origin right here at the bottom. As we'll see in a second, I'm going to want to express this in terms of x and y, and so that'll be easiest to do having it passing through the origin. All right, so we would be partitioning the y-axis, right? The problem here is the variation is vertical in that depth and therefore pressure, so that's our variable of integration. So we'd be partitioning through there. And then let's, as always, just look at one arbitrary partition. Say this is our y sub k minus 1 and our y sub k. We take some arbitrary c sub k in there and use the curve there at c sub k to determine our rectangle. And so let's approximate how much fluid force is on just that strip. Again, we'd have n of those going up and down. So remember, fluid force, weight density, depth, area. So let's figure out these three things in this particular scenario. Let's say that this is our typical water with a weight density of 62.4 pounds per cubic foot. So that'll be given, so that'll be easy, just plugging in whatever the weight density was for the particular fluid. Now we'll need how far under is this rectangle? Well, again, depends on where you are, right? Every little speck of that rectangle is at a different depth as we go up and down, but we're idealizing it as if it was all there at c sub k. So that's our approximation. So we're going from, how far is that c sub k from the surface? Well, let's look at our axis here. This is 0, c sub k. The top here was at 4. There's another 2 feet to the surface, so that's 6. So we're looking at c sub k up to 6. How far is that distance? So just the difference. So we got our weight density, which is 62.4, and our depth, which was 6 minus c sub k. Now, what about the area? Well, this dimension will be easy. That's just our change in y. What about the distance across here? Well, it's being determined by these two curves, and there's a symmetry here. This, from the axis out to this point, would just be x. All right, so this distance all the way across our rectangle involves an x and an x, or 2x. All right, so we know that the area there is 2x delta y sub k. But we're setting up an integral here with respect to y, right? We're going to sum these rectangles at various heights. So I want this x in terms of that variable of integration. And that's where this curve comes in here, this line determining that triangle. There's a relationship between x and y here. So what is the equation of this line? Well, this is where it's nice. It's passing through the origin. So we know that part of it. We just need to figure out the slope. It goes up 4 and over half of this 6, so 3. So the equation of that line is y equals 4/3 x, or x equals 3/4 y. So if you're at a y of c sub k, x is 3/4 c sub k. So 2 times our x, which is 3/4 c sub k, and then our delta y sub k. All right, so we've expressed an approximation. Now, let's think about this. That is the formula for force there, weight, density, depth, area. But there's some approximation that comes in right here when we start writing out the details, right? That's exact. That is an approximation, right? That all of this isn't at one depth. And also the area is an approximation, right? This rectangle is not the same as the triangle underneath it. So really emphasize at this stage of the game that that's where our approximation comes in because of that some idealizing that's going on there. Now, as we've always done, the force, well, add up all the little strips. And that would give us an approximation. We'd have a bunch of rectangles, add those all up, it becomes exact. We let the norm of the partition go to 0. And now I'll actually write in what that f sub k is, maybe simplify a little bit. 62.4, 6 minus c sub k, that's what, 3/2 c sub k delta y sub k. Now we have definition of a definite integral there. So our force is, now remember, this is where drawing your partition is helpful. All right, what are our limits of integration? People will often get confused, think, well, 6 is involved. Do I integrate from 0 all the way up to the surface, or where am I integrating? Well, what did you slice? You sliced up this triangle. You partitioned it. That's why I always draw that partition. Wherever you've made that partition, that interval is your interval of integration. So we partitioned the plate from 0 to 4. And that would be our integral then for the force on this plate. And you could take those constants out, distribute, and you've got a polynomial at that point. When we're done, what we've calculated now is a force. So what would let's think about what the units would be on this answer. This is force now. So in this problem, our units were distances in feet, and here we see our force units come in the definition of the weight density of pounds. So the units on this is pounds. All right, so always draw your coordinate system. That'll make sure you don't get lost on what your limits of integration are, or notice we had to get the equation of this line. If you don't have a coordinate system set up, you might not get that right, or you may not relate that line to the depth properly. So get a good picture first, and then draw your rectangle, and this should all come quite naturally from the rectangle.